When we did our Gettysburg Address sampling, you took a sample of 5 words and you calculated the average of those 5 words, and then we all took a little dot and put it on a histogram or a dot plot. That was a histogram of our samples, therefore a sampling distribution. Okay? A regular distribution is when you just have the individual word lengths in a, right? So this word was 5, this word was 7, this word was 2, and you put a dot for each word. That's a distribution. The sampling distribution is when you take a sample of 5, you find the average, and you put that average in the dot plot or the histogram. Or you take a proportion of your sample and you put that proportion on a dot plot. Okay? So remember, we have 2 important concepts. We have the population at large. Depending on what our population of interest is, it could be the entire United States. That's our population, and we talk about parameters that we know about the population, but most of the time we don't know the actual parameter. We don't know the average height of every American. We don't know the average cholesterol level of every American, but we can take a sample and use that sample to estimate the population. And when we take a sample and calculate those means and proportions, those are our statistics. Okay? So when we have parameters, that's the population, and our sample, a smaller subset of that population, is a statistic. So a sampling distribution is where we take different random samples. They give different values of a statistic, and the sampling distribution model shows the behavior of that statistic over all possible samples. Now here in chapter 18, we will be talking about both mean and proportions, but after chapter 18, we're going to focus solely on proportions from chapter 19 to 22. Okay? And then the next unit will work on just the means. Okay? So we're going to learn several different hypothesis tests and confidence intervals, but we have to know these basics to start. So the sampling distribution model for a proportion, okay, there are certain assumptions that have to be true. The assumption of independence and random sampling must be met. If we expect at least 10 successes and failures, then the sampling distribution of a proportion is modeled by a normal model. That 10 successes and failures comes from estimating a binomial proportion with the normal model. So if we have more than 10 successes and failures, then we can say that our sampling distribution is going to be normal, with the mean equal to the true proportion p, and the standard deviation equal to the square root of PQ divided by N. Okay? Remember that your AP formulas use 1 minus P, but that is the same as Q, right? I don't know what this weird little box with the question mark is. It just like appears when I import the PowerPoint. So, is there a hat in there? Okay, that's it. So the standard deviation of the proportion is PQ over N. For a mean, we have assumptions of independence and random sampling again, and the sample size has to be large enough for the normal model to apply. The mean is equal to the population mean mu, and the standard deviation is sigma over the square root of n. Okay, so these are formulas we will have to use. If there is a sample size, we have to divide by the square root of that sample size. The central limit theorem becomes really important in determining and allowing us to use the normal model. The central limit theorem states that the sampling distribution model of the sample mean and proportion is approximately normal for large sample sizes. regardless of the distribution of the population, as long as the observations are independent. Okay? Yes?
How do you tell between a large and a small sample?
So we're going to use a 25 as our number for a large sample size.
So anything above 25 is large?
Yes, anything above 25 we're going to consider a large enough sample size. Okay? So what this means is the population data could be skewed. If you think about income data, right? The data of income of the entire population of the United States is skewed to the right? We have a lot of people making between 0 and 100,000. We have a good amount making between 100 and 200,000, and less people making more than 200,000, right? And then you have that skew for the people that are making millions of dollars every year. But if I take a large enough sample size of the population and find the mean and create a distribution of the average of those samples, that sampling distribution will be normal, as long as my sample size is large enough. If I do a sample of size 2, pick 2 random people, find their incomes, average it, and put it on a graph, not going to be normal. If I take 25 and 30 people, average their income, put it on a graph, and I do that over and over and over again, that graph is going to be normal. If I take 100 people and average their income and do that over and over again and create a graph of it, that graph is going to be normally distributed. And therefore, we can use the normal model to make estimations and observations. When we estimate the standard deviation of a sampling distribution using statistics from the data rather than the parameters of the population, the estimate is called standard error, abbreviated SE. For proportions, it's P hat and Q hat instead of P and Q. For the mean, it's S instead of sigma, because that's our sample standard deviation. This we will use more as we move out of this chapter. It's called standard error, but that's not a mistake. Remember, there's always sampling error, how much we expect it to vary. So we have conditions for both. The conditions that are true for both proportions and means are 10%. The 10% condition is independence. As long as our sample size is less than 10% of the population, we can say that even though we're not sampling with replacement, our individuals are independent of each other. So 10%, there has to be randomness in both. I don't know why I don't have that written down. There needs to be randomness. And for proportions, success failure, that's NP greater than or equal to 10, and N times Q greater than or equal to 10. We worked with that last semester, the very end in chapter 17. And for the sample mean is N large enough. So we're going to say greater than or equal to 25. That's going to be our threshold for large enough. Okay. Independence is one of those things that is it reasonable to assume that each person's cholesterol is independent of each other? Well, yeah, if the sampling is random, then you're not getting like a dad and their kids, because it can be hereditary, then independence is a reasonable assumption. All right, so we drew normal models back in chapter 3. We're going to draw some normal models for a proportion based on the 68, 95, 99.7 rule. Says here that 80% of all cars on the interstate exceed the speed limit. What proportion of speeders might we see among the next 50 cars? So our sample size is 50, right? and our P is 0.8. We always convert our percentages to a decimal. We're going to draw a normal model to show, right? 80% of 50, yes, is 40, but that's not going to happen every single time, right? So how much does that vary? So for number 1, our P is 0.8, and our standard deviation is the square root of 0.8 times 0.2 over 50. Now this formula comes from the standard deviation of your binomial model, n times p times q, divided by the square root of n, and you do a little algebra and you get the square root of p q over n. So we have, let me find my calculator. Okay, so we put 0.8 in the middle, we added 0.0566 3 times, and we subtracted it 3 times. So here's our normal model for a sample of 50 cars. Now, what's going to happen to my standard deviation if this was a sample of 100 cars? Should my standard deviation go up or down? If I increase my sample size, meaning this number here, the 50, will my standard deviation increase or decrease? Decrease, right? If the number I'm dividing by is bigger, then my answer gets smaller. So the larger the sample size, the smaller the standard deviation, right? The less variation there will be. And the smaller the sample size, the more spread out our normal model is going to be. So it's very specific. In a sample of 50 cars, we expect between 74.34% and 85.66% of the cars to be speeding 68% of the time. So 68% of the time, we expect our sample of 50 cars to be between 74.34 and 85.66. And 68.68% and 91.32% of the cars to be speeding 95% of the time. I'm going to get a little lazy and use a little quotation marks across there. And we expect between 96.9, oops, let me put my lower number on there first, sorry. 63.02% and 96.98% of the cars to be speeding 99.7% of the time. So this is what we expect to get as our sample proportion in a sample of 50 cars. That's just like everything I said above. Yes? These two numbers should always add to 1, right? P times Q always add to 1, and you're dividing by the sample size. As your sample size gets bigger, the answer, the standard deviation, gets smaller. Okay, there's less variation in a large sample size. Okay. So number 2, we don't know it yet, but actually 52% of voters plan to vote yes on the upcoming school budget, we pull a random sample of 300 voters, what might the percentage of yes voters appear to be in our poll? So for number 2, our P is 0.52 and our N is 300. Take a second and calculate the standard deviation of the proportion. All right, so it's 0.52 P. Q is 1 minus P, so that's 0.48 divided by 300. And I got 0.029 or 88. Yes? Did we get that calculation? All right. Then take a second and draw your normal model. Just use 0.29, so 0.029, so you're not writing all these extra decimal places. All right, what do we get? 0.549. 0.578. And 0.433. Okay. So, in a sample of 300 voters, okay, here's another way to word it. 68% of the time, we expect between 0.491 and 0.549 yes votes. 95% of the time, we expect between 0.462 and 0.578 yes votes. And 99.7% of the time between 0.433 and 0.607 yes votes. Now this semester becomes really important that you model your homework well. The number one mistake I see when we do practice AP test questions and when we do AP questions on the tests is you're not following through with all of the steps because you're doing shortcuts when you do your homework. Okay, yes, it is a lot of writing. You are going to do a lot of writing this semester, more than you've done for a math class in your life. Okay, and possibly more than your non-math classes. Okay, but if you model correctly and do all of the steps correctly in your homework, then you're getting yourself ready to pass that AP exam. And most of you are signed up to take it. So, last problem here. What is the probability the school board poll, this is the second question on the next slide, makes the wrong prediction? What would it mean to make the wrong prediction? What we know is, and you usually don't know this, but 52% of the people are going to vote yes, therefore it's going to pass. So if the poll makes the wrong prediction, what is the poll going to say to the public? Can you say that louder? They don't think it'll pass. So what do they think the proportion will be? Less than 50%, right? So we want to know the probability that the proportion from the sample is less than 0.5. Because less than 50% would be a prediction that it's not going to pass when in fact it's going to. How do I find the proportion if I know a mean and a standard deviation? Nope. We know our mean is 0.52. We know our standard deviation is 0.29. I do not listen very carefully. I do not mix the two formulas. I do not use square root of PQ over N and then use sigma over N. You don't have sigma. You don't have the standard deviation of data that was gathered. You have the standard deviation of a proportion. We don't take that 0.029 and put it into the other formula. Okay? They're two separate formulas. If I have proportions, I use square root of PQ over N. If I have means, I use sigma over square root N. Okay? So I want to know what's the probability that I get less than 0.5. So I need to check my conditions. And this is where students get lazy. I can't spell. I need to check conditions. I always have to check to make sure the conditions are met so that I can appropriately use a normal model. If you forget to check conditions on the AP exam, you've lost a whole point on that free response question. And it's not a hard point to earn. Okay? So the conditions are sample is random. Is that true? Yes. It told us way over here that a random sample of 300 voters. The sample must be random in order for there to be independence. We're going to assume that 300 is less than 10% of all voters. That would mean 3,000. It's likely that this school district has more than 3,000 parents to vote, or this city has more than 3,000, so it's a pretty good assumption we can make.
I didn't get that. Could you try again?
No. And NP greater than or equal to 10, and NQ has to be greater than or equal to 10. This tells us our sample size is large enough. Okay, so that's 300 times 0.52. And 300 times 0.48. Now, you can say to yourself, obviously that's greater than 10. If you don't write down the actual number, they take points off on the AP exam. Yes. So you have to do 300 times 0.52 in your calculator and write down 156 is greater than or equal to 10. And that means 144 is greater than or equal to 10, because those two numbers should add to 300. Now I know that a normal model is appropriate, so since conditions are met, a normal model is appropriate. And we're going to use the z-score. I want to know what's the probability that they estimate, or their sample gives us less than 0.5. So 0.5 minus 0.52 over the standard deviation. Sample, or what you're asked about, minus your mean. Your mean is the proportion in this case divided by your standard deviation. Sample minus mean divided by standard deviation. That's not going to change. We're going to calculate z-scores. We're going to calculate t-scores. And they're all going to be the same idea. Your sample minus your mean divided by your standard deviation. So negative 0.02 divided by 0.029 is negative 0.68 97. And how do I get a proportion for a percentage from a z-score? Normal CDF. Oops. Oh my gosh. And is it negative 99 comma my z-score or my z-score comma 99? I want less than 0.5. So it should be negative 99, right? I'm interested in what's the probability that it's less than. And that's in your second distribution menu. We used it last chapter a little bit. And I get 0.245. So there is a 24.5% chance the poll makes the wrong prediction.